Good morning. I'm Paul Bremner from NASA Marshall Space Flight Center. Um, and I'm going to talk about something a little bit different. Whenever you're choosing what to put on a title slide, you want to choose a figure that sort of encapsulates everything you're going to talk about, right? So this figure over here, I think does a pretty good job of it. It's old now. It's from Renee Weber's 2011 science paper. But rather than just talking about the surface of the moon, we're actually going to talk about the entire interior of the moon. And so we take measurements from the surface and see what we can deduce about the interior. And when I say interior, I mean a couple of different things throughout the talk. And so interior at the beginning is going to talk about things like mineralogy throughout the depth of the moon. But there's also another story wrapped up in here about the temperature. And so when I talk about the lunar interior, I'm also talking about the temperature. So this is an interesting result. It sort of fell out. We didn't expect it. I'd also like to acknowledge a couple of the collaborators, specifically the students and postdocs. So we have Arkadeep Roy over here in Arizona. We have Matthew Diamond. He's a postdoc over in Chicago. And over here, we have Han Byul Woo, also known as Aiden. He's at Marshall Space Flight Center as a postdoc there. Okay, so there is a seismic component of this. My background is as a seismologist. And just starting with the Apollo astronauts, they deployed multiple instruments on the lunar surface through the ALSEP. And what you see in this image right here in the forefront is actually one of the seismometers that were deployed. These are passive seismometers. They just passively recorded thousands of moonquakes, actually. And for about 5 years, 4 of those broadband stations passively recorded moonquakes. And the results that came out of it were the ability to measure first arrival P and S seismic travel times. And so here's a couple of examples of the models that were generated. The seismic data is notoriously messy. It's very hard to work with. But by being able to measure those first arrivals, there was the ability to generate some lunar profiles. So these dashed lines here are S velocity. And the important thing to know about this, sort of a theme throughout the talk, is that S velocity is very sensitive to temperature. These solid lines, these are the P velocities. And of course, they are always faster. So the P waves arrive at the station first for the non-seismologists out there, and then the S waves arrive soon after. And the travel time that we talk about is exactly that, the time it takes to go from the moonquake to the station. Well, over there on the back monitors, you'll see a gray region. It's not showing up on this at all, so apologize for that. So one of the things that you can do with the seismic data once you have it is through a series of assumptions, you can infer a you can infer a temperature profile going through the moon. And so some of the assumptions that you need to make have to do with things like mineralogy. Now, seismic data is not the only way to get at this. There's other geophysical data that was collected, including electrical conductivity and gravity. And in a similar way, you can, through a series of assumptions, create a thermal profile. Now, what you don't see is, unless you look at the back monitors there's a large gray region here. So what I've done for the sake of time is go ahead and integrate all of those thermal profiles together into one gray region. And the point is, if you can imagine, that the region is quite large. So the problem is not well constrained. So these over here that you can see are actually at the hotter end of those profiles. And the problem is more absolutely bounded towards the upper end of those temperatures. The reason being is that the seismic data and other geophysical data doesn't really indicate melt throughout the majority of the mantle. Not until perhaps the very deepest portions of the lunar mantle, maybe even at the core mantle boundary. And so we have some bounds for the upper end, but what we don't have, once again, if you can imagine the thermal profiles going through here, is we don't have anything to help bound that lower end. So we don't know how cold the moon is. And so that's part of the story that I hope to convince you fell out of this work. So what we did was we did a lot of hypothesis testing. So portion of this is a modeling exercise. So we generated lunar interior models and we tested them. And so I'm just going to quickly walk you through exactly how I generated these models. And I will walk through kind of quick, but I'm happy to answer any questions after the fact about how we generated these. But I want to leave time for the result at the end. I'm going to walk through this sort of flow chart on the left-hand side. And the idea here is that we're doing an iterative forward modeling approach. So we're doing hypothesis testing. We say, suppose the moon looks like this. Let's go ahead and calculate its properties and see what we get. The main advantage is that we're able to combine a lot of different data sets that are typically very difficult to combine together. So this is that gray region that you can't see again. So I apologize for that. The idea is that you need a couple of ingredients to start with. You can impose a temperature, and you're about to see some profiles pop up here. So now you can actually see the span of that gray region. So what we did was that gray region that's in here, in order to be able to start from somewhere to something, we wanted to bound the problem. So this cyan dashed curve right here that's the minimum portion of that profile, and then the red is the maximum portion of that. And then of course the yellow is just right in between, it's the mean. And these temperature profiles are the ones that we moved forward with and tested. We also want to be geologically informed, so we create a profile of mineralogy throughout the entire moon. And don't focus so much on the details of what the minerals are in each of these. The thing to know is that this here and this one here, so the two on the left, represent a different dynamic history of the moon's interior. So where a lot of mixing has occurred and the bulk composition throughout the mantle, it's really homogenized. So things have mixed thoroughly. On the right-hand side, what we call the stratified, it hasn't mixed thoroughly. So this is if the moon just formed, came together, and a magma ocean cooled peacefully and no mixing occurred. With the exception of, it's hard to read, but we have this special layer we call the upper ilmenite and lower ilmenite. And that has to do with the possibility of what's known as an overturn, where a layer at the top sank to the bottom of the lunar mantle. And it's just an iron titanium rich ilmenite that looks very similar to the layers just beneath. And so the idea is that we're here at this stage, we're just selecting these. And now what we want to do is we want to start up our search algorithm, right? So we choose one of those profiles and we choose the temperature profile right here. And notice I don't have any thicknesses on here. And so this is what happens. We go ahead and choose those. And this is somewhat random. We choose some thicknesses. And that allows us to then go ahead and start calculating some properties. Thank you. Okay, I need to speed up. These properties right here, are calculated through mineral physics software known as Bremner. And we can make an assessment of how those did by comparing to actual observational data. So here I'm comparing the total planet mass and moment of inertia. And the idea is that we can then iterate by choosing new thicknesses. And we iterate many, many times. Lots of times, actually. We ended up with some 400,000 models that we tested. And we went ahead and checked the mass and moment of inertia plus some other metrics. And that's what this plot is showing here. Each dot, the color is just representing how many models are stuffed in there at each point. And the axes are telling you standard deviation between mass and moment of inertia. And so you want to be here at the bullseye. The closer you are to that, the better. And there were 186 models out of those 400,000 that made it through that. And so what we were looking for originally was a way to filter this down even more. And so we used the seismic data and started mapping out the travel times. We started modeling the travel times using the moonquake locations and station locations from actual data, but combining it with these seismic profiles. And so that's what these are representing. I apologize, the plotting software sort of bundles all of these stars, the sources, the moonquakes, together instead of the stations, which are these triangles. But it samples different portions of the mantle. So this is depth, and this is distance away between station and moonquake. So the process was successful. It got rid of 80% of those 186 models that we were left with. So that part is great, but and I'm happy I was able to get to this, but this is the thing we didn't expect. So this is subtracting the travel time of the S wave and the travel time of the P wave from each other, just looking at the difference. The X is our actual data. That's from the catalog. And then these symbols over here, the triangle, square, and star, those are the different petrologic and thermal profiles that I tested. And what's interesting is that they start to deviate as you get further away. So this right here is distance between source, the moonquake, and the station. And as you get further away, they start to drop out from the X's. And what's interesting, I thought I needed to go ahead and replace these labels, and then I promptly forgot to do that. So this model type 1 up here is one particular petrologic profile and a thermal profile. It's the mean thermal profile. And this square is actually the colder one. And the star is what we call the stratified petrologic model, and once again, the mean. And the star and the triangle, they overlap with each other. Whereas the colder model does not, it deviates. It has a further separation between our actual observed data and what we modeled. And so what this means is that if your moon is too cold, you actually have a worse fit than if your moon is a little bit hotter. So this is giving us a lower bound on our temperature profiles that we didn't have before. What's interesting is that 60 degrees right here, distance, is sort of a demarker. If you're closer than that, where the moonquake is much closer to the station, then your fit is actually not bad. But when you're further away, you get more and more deviations. That could either be just you need more time to resolve that, or maybe there's some differences in the upper and deeper layers of the mantle. And just in the interest of time, I'm going to skip that slide and go over to here. And I'll even put that up, but we're not quite satisfied that we're going to write this up just yet. We have some more things, and I'll leave you to read that. So thank you.
Thank you so much, Paul. I'm afraid we don't really have time for questions. So if you have any, please go see Paul.
Yep, I'm happy to answer anything later on.
So let's switch to our next speaker. And this is Jean-Pierre Williams talking about the Faustini permanently shadowed region observed by the KPLO shadow cam instrument.